Okay, welcome everybody. This is Dr. Pingle back again for the first lecture in the series, Cartography and GIS, Making Better Maps. So what we want to talk about today is how we can get a hold of some basic data, represent that, but do it in probably a better way than maybe you're used to. It's very easy to create maps in GIS, but it's a little bit harder to create good ones. And that's one of the skills that you really need when you're going out there looking for a job. You want to make sure that you've got a good track record, a portfolio, something that you can show people to let them know that you know what you're doing. And making good quality maps is a lot like writing. You really just want to kind of put your best foot forward. The better you can incorporate some of the techniques that I'm talking about today, the better your maps are going to look in the end. So with that, let's move on. All right, I'm going to cut out the video portion of this. Oops. All right, so one of the first points to emphasize is that everything that goes on your map needs to be there for a reason. So this is a fairly lengthy quote that's getting at that idea. And if you take a look at it, it says, think carefully about every element. Does it play an essential function? Could it be simplified? Does it require elaboration? Is it of critical importance to reader comprehension? All of these things are important. Everything that's on a map should be there for a defensible reason relating to message and audience. And it's really hard to overstate that. We'll look at this when we go through your map submissions. So your first assignment, you're going to submit things. We're going to take a look at those. Really, you'll be surprised at what's on there that doesn't need to be there, and what is perhaps missing that probably does need to be there. And these are all things that we're going to learn as we go through and review maps, and we'll do some of that at the end of this lecture series. We've kind of divided this up. Cartographers have divided this up into four main topics. These are the four that I want you to emphasize when you're creating maps for class. So one is scale and projection, and this is probably the easiest ones for beginners to maybe make a mistake on. It's probably the easiest mistake for someone reviewing your map to sort of pick on. But you really want to make sure that the scale is appropriate for what you're showing, that the extent, how much map area there is appropriate for the story that you're trying to tell, and the projection suits the goals that you're trying to accomplish. The second element is visual hierarchy. So this is a term that describes the ordering of elements in terms of importance. So certain map elements like titles, like theme symbols are more important than others. And you're going to want to make sure that you're using colors and placements that make sense to make the most important map elements stand out. Symbology. Every map that you're going to make is likely to have some kind of symbology. And what we want to try to do is make sure that the symbols that you're using are evocative in some way, that they match the story that you're trying to tell. You'll see some examples of this, but the more you can reduce the work on the user to have to go and refer to the legend to figure out what you're trying to say, the better. And then finally, you want to make sure that you've got good balance with the maps that you're showing. Balance is sort of like interior design. You want to make sure that you've got a good sort of dispersion so that one part of the map doesn't feel overcrowded or heavy, and that you're really using the space effectively. This one's kind of a hard one to describe, but it's an easy one to spot when you're doing it. So let's take a look at these in turn. We'll focus on scale and projections first. So projections are something that you've probably seen a good deal before in previous classes. So this is just kind of a quick review, making sure that everyone understands the issues that are involved. And so first of all, it's important to realize that every map that you're going to be working with is projected in some way or another. Every time we want to take a round Earth and put it on a flat screen, we're going to need to reshape that data. And the way that we reshape it is the projection. And there are hundreds, thousands of projections out there. You only really need to know a handful of these. But it's good to know where you can find out more information. You never really know when you're going to run into something a little bit strange. But there are probably, like I said, so 3 to 5 projections that are kind of used day in and day out to get most of the work done in GIS. There are classes of projection. So we've got a couple of major types. One of the major types is an equal area projection to make sure that landforms are represented on a map proportionally to what they actually are. We've got conformal projections that preserve local shape and direction. And in some cases, we've got maps that sort of aren't either one of these two main classes. Those are called compromise projections, where we're trying to sort of leverage one of these against another to have sort of more maps that sort of tell a story for a particular purpose. And we'll look at a Robinson projection that's a good example of this. It's not equal area, it's not conformal. It sort of fudges both of those criteria to effectively communicate the shape of the Earth. This map that we've got over here at the right is Fuller's Dymaxion map. It's one of these compromise projection. It's not equal area, it's not conformal, it's a funny shape. It's sort of the Earth carved up into this sort of interesting semi-discontinuous form. Very pretty, especially with the satellite composite image here. But it's heavily interrupted, right? So it's not all that particularly useful for things like wall maps, but it is quite clever, and it does do a good job of sort of showing relative size. Probably one of the projections that you're most familiar with is the Mercator projection. So this was a projection that was originally intended for navigation. So the idea behind this is that we could we can draw a line connecting two points that we wanted to go to. So we could draw a line connecting, let's say, Boston with London. And the idea is that the old sailing ships could figure out what that compass bearing is, dial it in on their compass, follow that route, and they would wind up there. Now, the interesting thing is that this is not a shortest path. So again, we're taking the round Earth and we're turning it into a flat map. And the straight line between them drawn on a Mercator map is not actually the great circle distance or the shortest distance between 2 points, but it will get you there. It's the easiest to navigate, and that was the original purpose of this map. It's certainly not an equal area projection, so things like Greenland, anything very north or very south is heavily distorted in terms of area. So Greenland, which is fairly big, is not quite this big. Russia, a very northerly lying country, is big, but it's not quite as big as it appears here. In contrast, places that are along the equator are going to appear relatively smaller than they actually are. So one of the criticisms of this map is that Africa appears much smaller than it actually is. On this map, it looks probably smaller than all of North America, but that's definitely not true, and we'll show you that in the next slide. One of the interesting things about this, because it preserves shape locally, but not area, so it's conformal, is that when you zoom in on it, shapes of things locally are actually going to look fairly good. So despite the fact that there's distortion over sort of the global scale, at the local scale, things kind of look as they should. So the advantage of this is that for web maps, you can zoom in on these things on like Google Maps, or even most of the tiles that you're using on ArcGIS Online are going to be stored in a web Mercator projection, a slight modification of this. But once you zoom in, the city is going to look sort of shaped like it ought to, and that's definitely not the case if you just sort of load in a raw shape file. This is an example of what that looks like. So this is part of DeKalb. If we took an aerial photo of this, minus a little bit of distortion around the edges, this is more or less what we would see. So scale ends up looking relatively constant across relatively local areas on a Mercator projection. The transverse Mercator projection forms the basis of one of the major coordinate systems that you need to know, and that's the Universal Transverse Mercator Coordinate System. So a normal Mercator is a cylindrical projection. We take a cylinder, we wrap it around a globe, and we unravel it. In that case, the cylinder is aligned with the poles. In this case, the transverse of Universal Transverse Mercator means that it's sort of 90 degrees opposed to the direction of the poles. So it's still cylindrical. And because it's exactly the same projection, essentially, as the Mercator, just oriented differently, and has all the same properties. So it's not equal area. it is conformal. And the interesting thing about this coordinate system is that if we take each of these cylinders and we rotate it at 15 degrees each time, we can create very locally accurate systems. So the idea is that anywhere the cylinder sort of touches the meridian, you're going to have the lowest amount of distortion. And so the Universal Transverse Mercator Coordinate System is an attempt to create a global system of projections that's all fairly accurate locally, but not very accurate necessarily globally. One of the cool things about this projection is that it basically reflects the exact same distortions that are present on the Mercator projection that you see here. But because you're more used to seeing this map, and you're a little less used to seeing this map, it's actually very helpful in identifying some of the kinds of projection distortions that are happening with this, that are happening just as much here, but you don't notice them because they're kind of hidden away. The reason, again, that we do this is that distances are only accurate within about 15 degrees of the central meridian. That's sort of a ballpark figure, one that geographers have been comfortable with. And so the idea is that by staggering, by creating many of these projections in different zones, all spaced 15 degrees apart, we can create a series of locally accurate maps. These are the UTM zones in the United States drawn on top of a Lambert conformal conic projection. This part of Illinois is in zone 16. UTM applies differently in the northern and southern hemispheres, so we're in 16 north technically. And you can see the different divisions across the United States going from zone 10 in the west coast to zone 19 by the time you get to Maine. This is a map of what that looks like globally. So in many cases we reference certain grids of these in reference to a letter. This isn't actually commonly used for a lot of mapping, but you will see it occasionally, so it's good to know what that might mean. Again, most of the time what you'll see is the divisions being given in terms of the zone that you see here. So once again, in eastern Illinois or northern Illinois, we're in zone 16. So most of the time we would reference this as zone 16 north rather than, let's say, 16T. But once in a while you'll see it, especially in military applications. We've sort of got at this just a little bit before, but on this map, this is the UTM zones projected on top of a Lambert conformal conic projection. As probably a refresher here, conic projection means that we're using a cone as the developable surface. We're kind of placing that on top of the globe. There are two ways that we can do this. If we imagine the Earth as a solid surface, once that cone hits it, it's gonna stop. So this is going to be something like a tangent cone. But we could imagine that if we could sort of sink that cone in through the Earth's surface, we could get it to be touching that Earth's surface at 2 points, in which case it's a secant projection. Now this is kind of important because wherever that developable surface touches the Earth, you're going to get the minimum amount of distortion. So if you only hit once, you're going to have distortion that's low, kind of in one ring on the conical surface. But if you can sink it through the Earth's surface, you can get 2 points where it's going to touch, meaning you've got sort of two zones where you've got the least amount of distortion. So for many reasons, when you look at conic projections and you're using those, you'll often be using two parallels rather than just one. Conic projections work really well for regions, so especially in North America, we use the Lambert conformal conic pretty often. We also use the Albers conic projection in some cases. Both of those are pretty good at presenting regional areas with sort of a minimum amount of distortion. This is an example of what Albers equal area conic. Equal area, obviously, the landforms are going to be true to size, which can be important later. This is an example of what the Lambert conformal conic projection looks like. Nearly identical, some minor differences that you can sort of make out when you see them laid against one another. But on both of these projections, we're using 2 standard parallels, meaning both of these are secant projections. When you line these up one on top of another, so in this case we've got the Lambert conformal conic, which we just looked at. We've got the Mercator projection in red, and we've got what we would often call unprojected latitude and longitude in green. And so this helps you sort of see how the shape of the United States or the lower 48 look when you compare these. One of the things that you'll notice right away is that both the Mercator and the unprojected system use a straight line here. So we've got a line of latitude that separates the United States from Canada. That line of latitude appears like a straight line on this. And that's not true for the Lambert conformal conic. That bend in the cone that we saw in the previous graphic shows up here as sort of a bent top. And we have to mentally sort of transform that into the straight line that it actually is. A note here, so when this says unprojected latitude and longitude, this is a bit of a misnomer. Unprojected in this case means that we're spacing latitude and longitude equally. We're sort of treating them as if they're a Cartesian coordinate system. 1 degree of latitude is going to be given exactly the same distance as 1 degree of longitude, which if we go back and take a look at the Mercator projection, that's not actually happening. So you can see that near the equator, 1 unit, in this case this is probably 15 degrees worth of latitude and longitude, ends up looking like a square, but by the time we get northward, we can see that what's still 15 degrees here is a much different distance than 15 degrees there. And under the quote-unquote unprojected latitude and longitude system, which is sort of the default coordinate system if you just start naively bringing in a shapefile that doesn't have a projection information attached to it into ARC, that's what you're going to get, sort of this equal spacing. This is one of the most useful projections for showing maps of the world. This is the Robinson projection, named after one of the great cartographers from the University of Wisconsin. This is a compromise projection. This is neither conformal nor equal area. It doesn't do a particularly good job of doing anything well, but it does do a great job of giving you the overall picture of the world. This is one of my favorites, and I would encourage you, when you're making some maps, to consider using the orthographic projection. So the orthographic projection is sort of like a perspective view of a hemisphere. You get high distortion over here at the edges as that curved surface sort of bends around by sort of like the horizon of this image. But it does a really good job of sort of showing local areas. So if we wanted to sort of look at the United States, we could use an orthographic projection and do that. Sort of a nice way to sort of make it look as if you're looking at the Earth from space. Again, this is a map of the lower 48 states in unprojected coordinates. Hopefully this looks stretched out to you. So we've got the United States kind of stretching east-west a lot more than it should. And that's because lines of longitude kind of come together near the poles. And so they aren't spaced equally. And so when you do space them equally, it has the effect of, if this sort of should be a triangle, has the effect of sort of stretching it out. And that's why we get this sort of east-west distortion in the United States. You should really be careful not to use this projection for pretty much anything except preliminary data analysis. It's okay to bring this stuff in to sort of take a quick look at your data set. But you don't really want to print this out and show it to people unless they're other geographers and they know that you're just doing some preliminary analysis. It's really no excuse to just go ahead and put this on your map. So avoid that if you can. This is a really nice poster. So the USGS, a lot of the images that I've shown you come from this very nice U.S. Geological Survey poster that was made several years ago. I've got a link for that down at the bottom, and that'll be in the PowerPoint presentation that you can access anytime. You can buy a copy of this, but you can also download it as a PDF for free. Very, very nice map. So I'd encourage you to, at least if you have some time, download it and take a look at it. This corner down here gives some nice information about suitability for projections. So as you're learning how to decide which projections are good for a particular purpose, we've got all of this nice list of projections here. We've got properties of these, whether or not they're suitable for mapping, and what general usage they're for. So very nice sort of summary of how you should use these. You don't have to memorize that by any means, but it is important that you probably know the difference between the Mercator, the transverse Mercator, which is the basis for the UTM coordinate system, and probably know a little bit about things like the Robinson projection, the orthographic projection, and the two conic projections that we looked at. Finally, we want to talk a little bit about scale. So you should be aware that every layer that you're going to use is only going to be appropriate at certain scales. So the resolution of your data set is going to dictate sort of what scale it's appropriate to use that for. So for example, how many points do we need to faithfully represent the United States boundary? Could we do it with 100? Do we need 1,000? Do we need 10,000? Well, the answer always depends on how am I planning on showing the map. If I'm showing it on a phone screen and not using it for sort of high-resolution imagery, then I can get by with a lot fewer points than if I'm making a map that's going to hang on the wall and is 8 feet wide. So you really need to be careful to sort of think about the purpose that you're intending the map for, and adjust the cartography accordingly. You can always sort of sample down, so you can take a high-resolution vector file and you can reduce it with simplification algorithms. In fact, that's going to be a part of your assignment for this section. The notebooks are going to ask you to use some of the line simplification tools that are in ARC to get a sense of how this can be done. But there's a really nice website to sort of give you a brief idea. So Mike Bostock is one of the sort of leaders right now in the geovisualization community. Comes up with a lot of really great examples, a lot of really great blog posts that illustrate some of these basic concepts really nicely. In this case, we've got a map of the United States. It's telling you how many points we're using here. The data source, which we're going to be talking about here in a second, is natural Earth. So bear that in mind. The original data set coming in at 1 to 10 million resolution. Now, the interesting thing is, as I move my slider back and forth, I'm using a certain percentage of this. It's actually applying a line simplification algorithm to the full data set as I move the line across. And one thing to notice here is that as I move the cursor further to the right, it's simplifying this. As I move it further to the left, we're densifying it. But there are really good reasons not to just use the most dense image that you can get a hold of. So I said that particular data set comes from Natural Earth. Natural Earth is one of the key data sets that we're going to be using as part of this course. So www.naturalearthdata.com/downloads. If you just Google Natural Earth, it's going to be the first thing that comes up. Natural Earth is a spectacular data set that is developed by NASIS, the North American Cartography Society. They have sort of in the past couple of years put a lot of effort into developing some freely available data sets that you can get a hold of that represent cultural features, physical features, and also some really nice raster features that you might need. And you'll notice that these are being distributed at 3 different scales. So we've got a scale here for large-scale data, 1 to 10 million, and this says that it's suitable for making zoomed-in maps of countries and regions, or if we wanted to show the world on a large wall poster. We've got medium-scale data, so if we were looking at zoomed-out regions. And then we've got small-scale data, 1 to 110 million, suitable for schematic maps of the world on a postcard or as a small locator globe. So different resolutions for different purposes. So the question is, why would we ever use something that was worse resolution? Why does it ever make sense to do that? In this case, this is a good illustration of the boundaries of Iowa at 2 different resolutions, again taken from that natural Earth data set. So this is in red, 1 to 10 million, in black, 1 to 110 million. So the black is a much coarser resolution. The red map, you can really see a good bit of detail, especially in some of these regions in western Iowa and around the border here. So the question is, why not use the highest resolution data that you can find? Well, the reason is that when you take high resolution images and you zoom in and you zoom out on those, you're going to get some sort of overwriting of lines. So as sort of, especially on the coastline here, these lines sort of double back on themselves. You get this sort of odd redrawing and effectively smearing of the coastline here that's not particularly attractive. So you're not really getting the benefit of your high resolution data set. In fact, this probably looks worse. So this is a good argument for trying to make sure that you make an effort to get the resolution of data that's appropriate for the visualization that you want to show. If you go to the census, so the census is one of the great resources for downloading not just population data, but a lot of demographic data, data about people, so economic, crime, all kinds of good information can be gathered from the census. They distribute these in a couple of different versions. If you just sort of naively go to the census and look for shapefiles, you can certainly download those. But you want to be a little bit careful. They've got these cartographic boundary shapefiles that they pre-prepared for exactly this reason, because they know that the resolution that you need is going to depend on the story that you're trying to tell. And so they've sort of pre-prepared, pre-simplified some of the boundaries. So be thinking about that when you take a look at your next assignment. Think about what places are going to be most appropriate. The census distributes these in a couple of different scales. So the generalized census files you can download at 1 to 500,000, 1 to 5 million, and 1 to 20 million, so that you can see there's some overlap in terms of scale, but the census files are a lot more on this side and don't go to this 110 million. It's really only suitable for global scale projects. As part of your Notebook 1, you're going to be using some of these tools. So you're going to be using the Simplify Line, Simplify Polygon, Smooth Line, and Smooth Polygon. A couple of different ways of taking high resolution data and making it more suitable for visualization at a smaller map scale. You do have to be a little bit careful. Automated tools can create odd results. So I wouldn't, for instance, recommend just grabbing sort of the highest resolution census file and then applying these tools if you have those nice pre-prepared layers for you. If you don't, then you use what you've got. You've got to go ahead and use those. But if you can get a hold of pre-prepared scale, pre-prepared layer at a certain scale, then you should definitely do that. So we'll wrap this section up. The next section is going to be visual hierarchy, so stay tuned for that.